There was a time when the ocean existed without a single human sound above it. No engines crossing the surface, no sonar penetrating the depths, no human voice anywhere on Earth, only warm water pressing down into darkness, and predators moving through a world that belonged entirely to them. 60 million years ago, one of those predators belonged to a shark dynasty whose most famous member would not appear for tens of millions of years. Megalodon was not the beginning of that dynasty, it was the end. By the time Megalodon appeared, members of its lineage had already been hunting the world's oceans for tens of millions of years. The earliest sharks in that chain had survived something Megalodon never would, the asteroid that ended the age of dinosaurs. They were not enormous. They did not overpower the catastrophe. Somehow, their size, habitat, and feeding strategy placed them among the survivors, and the predatory blueprint they carried continued into the oceans that followed. Then the lineage began producing giants. One of Megalodon's ancestors was already hunting early whales, while those animals were still completing their transition from land to sea. Some of its prey belonged to a world in which whales still had functional legs, and later members of the dynasty entered oceans containing rivals Megalodon itself would never encounter. For millions of years, enormous predatory whales shared the same waters with these sharks, including forms approaching 65 feet long. In that ocean, being enormous did not guarantee that nothing enormous could hunt you back. Yet the shark lineage continued through extinction, through cooling oceans, through disappearing prey, through entire groups of marine predators rising and vanishing around it. The lineage did not build toward one monster, it built several of them, one after another. Eventually, the final ancestor before Megalodon became so similar to its famous descendant that scientists have debated exactly where one ends and the other begins. The teeth changed, the body grew, the oceans changed with them, and after surviving upheavals that erased creatures far more famous today, the dynasty eventually produced the largest and most specialized member of its entire history. That was the one the world finally broke. Megalodon is the shark everyone remembers, but its ancestors survived worlds Megalodon never had to face. In this story, we're following that forgotten lineage through the ancient oceans that created it, the predators that challenged it, and the survivors that eventually produced the most famous shark in history. If you enjoy uncovering the stories behind some of the most extraordinary predators ever discovered, give the video a like and subscribe. Now, let's go back to where it all started. Imagine a shoreline that no longer exists, where waves rolled across places that would one day become Kansas, Texas, broad regions of Europe, and much of Africa. Around 100 million years ago, during the late Cretaceous, the sea reached far beyond today's coastlines. Water stood roughly 330 feet higher than modern levels, spreading across continents in wide inland seas. Earth carried no great polar ice sheets, and warm conditions stretched from the equator toward the poles, giving marine life an enormous realm in which to flourish. One of the greatest waterways of that age was the Western Interior Seaway. It reached from the Arctic Ocean to the Gulf of Mexico, dividing North America into eastern and western landmasses. Fish, reptiles, and sharks crossed its immense corridor, while currents carried nutrients through waters that often reached between 85 and 90 degrees Fahrenheit in tropical and subtropical regions. Life filled nearly every layer of this marine world, leaving little room for hesitation. Every movement through open water carried the possibility of meeting something larger, faster, or better armed. The upper ranks of this ecosystem belong to an extraordinary collection of hunters. Long-necked plesiosaurs glided between schools of fish. Powerful plesiosaurs relied on immense jaws built for crushing prey. Mosasaurs, giant marine reptiles that could approach 50 feet in length, patrolled the open sea with confidence earned through strength alone. Giant sea turtles drifted through these waters beside massive bony fish, while ammonites, some as wide as automobile tires, floated through the currents in astonishing abundance. Countless predators occupied every level between the smallest fish and the greatest reptiles, creating an ocean where competition shaped every generation. Within such a crowded environment, an apex predator occupied the highest position in the food chain, facing little danger from natural enemies after reaching adulthood. Even so, supremacy depended upon opportunity as much as power. A hunter could dominate one habitat while remaining vulnerable elsewhere, especially in a sea overflowing with specialized rivals. Success belonged to creatures that balanced speed, endurance, efficient senses, and the ability to exploit changing conditions whenever they appeared. Among these many hunters lived a group known as lamniform sharks. Modern relatives include familiar species such as the great white shark and the short-finned mako, though the family reached far deeper into time than either living example. Members of this lineage shared distinctive tooth arrangements, streamlined bodies, and jaws designed for swift attacks. Their skeletons, however, consisted mostly of cartilage, a flexible material that almost never survives the long journey into stone. For that reason, teeth have become the lasting record of their existence. Sharks replace their teeth throughout life, leaving thousands behind across the sea floor. Each preserved crown carries details of shape, cutting edge, root structure, and wear that reveal relationships between species separated by millions of years. Vertebrae occasionally survive as well, offering hints about body size and growth, though they remain far less common than teeth. Through these scattered remains, paleontologists can follow an evolutionary thread stretching across immense spans of time. Hidden among the countless hunters of the late Cretaceous swam one modest shark lineage already establishing itself within this demanding world. It claimed no title as the largest predator, and many neighbors exceeded its size with ease. Even so, its design allowed it to endure, laying the first enduring foundation of a dynasty that would continue long after the marine reptiles disappeared from Earth's oceans. Among the countless fossils scattered through rocks of the early Cretaceous, a single tooth pattern appears again and again with remarkable consistency. It belongs to Cretalamna appendiculata, the earliest well-established ancestor in the lineage that would eventually produce Megalodon. Its story begins around 105 million years ago, when the oceans supported an astonishing variety of hunters, each adapted to a particular place within an already crowded world. By modern standards, this shark appeared almost modest. Adults likely reached between 8 and 12 feet in length, placing them close to the size of a large living bull shark. Nothing about its body suggested the giant descendants that would one day dominate marine food webs. It relied on balance instead of overwhelming size, moving through coastal waters and open seas where larger reptiles often occupied the highest ranks. Every successful hunt depended upon timing, agility, and an anatomy refined through countless generations. Evidence of its presence reaches far beyond any single shoreline. Fossils identified as Cretalamna appendiculata have been recovered from North America, Europe, Africa, and Asia, making it one of the most geographically widespread sharks known from the Cretaceous world. Such an extensive distribution hints at an animal capable of thriving under many different conditions while remaining closely tied to warm seas. Populations separated by entire oceans still carried the same distinctive dental features, preserving a recognizable identity across enormous distances. Its name reflects both its age and its family ties. The first portion honors the Cretaceous period during which it flourished, while the second recognizes its relationship with lamniform sharks. Although the body itself has almost vanished from history, the teeth preserve an extraordinary amount of information. Each tooth carries a broad triangular crown rising from a sturdy root, accompanied by tiny side points called cusplets. These delicate projections appear almost decorative at first glance, though they would become one of the defining signatures of the entire lineage. Paleontologists follow those cusplets through millions of years, like familiar handwriting preserved in stone. Later species altered them, reduced them, and eventually lost them altogether, yet their earliest appearance forms a reliable connection between distant relatives. Even when body size changed dramatically, this inherited design revealed that the lineage remained linked through deep time. The famous giant teeth of Megalodon would still echo this ancient blueprint, enlarged beyond imagination while preserving its underlying geometry. Life for Cretalamna appendiculata unfolded beside predators capable of ending it in moments. Mosasaurs, plesiosaurs, and other formidable reptiles shared the same waters, occupying positions far above this shark in size. Survival depended upon avoiding unnecessary encounters while pursuing prey suited to its own abilities. Large bony fish, rays, smaller marine reptiles, and perhaps young mosasaurs likely formed much of its diet, providing enough energy without demanding impossible risks during every hunt. Its lasting success rested within that practical design. The body remained efficient, the teeth versatile, and the range exceptionally broad. Across nearly 50 million years, those strengths required remarkably little alteration, suggesting that evolution had already assembled a predator well matched to its surroundings. Many larger creatures came and disappeared during the same span, while Cretalamna appendiculata continued its patient passage through the Cretaceous Sea, carrying forward the foundation from which an entire dynasty would gradually emerge. A predator's future can sometimes be written in a feature small enough to rest in the palm of a hand. For this lineage, that feature was the tooth. While muscle, skin, and cartilage disappeared with time, the teeth remained, preserving the design that carried these sharks through changing oceans. Each fossil reveals an engineering solution refined long before giant bodies appeared, showing that success first emerged from anatomy instead of size. Many sharks of the Cretaceous possessed narrow, pointed teeth suited for grasping slippery prey. Such teeth worked much like hooks, holding fish until the jaws could finish the struggle. Cretalamna appendiculata followed a different path. Its teeth formed broad triangles, rising from sturdy roots, creating a shape far better suited for slicing than piercing. The cutting edges met prey with concentrated force, opening flesh cleanly instead of relying upon prolonged grip. That distinction became one of the defining characteristics of the lineage. This design encouraged a hunting strategy unlike simple capture. A fast strike could remove a substantial piece of tissue before the shark released its target. A wounded animal lost strength through blood loss and exhaustion, while the hunter remained at a safer distance. Such an approach reduced the danger of wrestling with struggling prey that might possess sharp fins, crushing jaws, or defensive armor. The effectiveness of each attack depended less upon overpowering an opponent and more upon where those cutting edges landed. Because of that advantage, body size alone never determined success. A predator, equipped with efficient cutting teeth, could challenge animals larger than itself if it delivered well-placed bites. That principle echoed through the lineage across millions of years. The earliest members established the mechanical foundation that later descendants would expand on an extraordinary scale, all without abandoning the essential geometry already present in these modest ancestors. The jaws supported this strategy just as effectively. Cretalamna appendiculata carried a subterminal mouth positioned slightly beneath the snout, allowing the upper jaw to project over the lower one. This arrangement created a broad gape capable of closing securely around substantial prey. Although the shark itself measured only several feet in length, the leverage within its jaws produced impressive force for an animal of its size. Every movement reflected a predator, adapted for decisive contact rather than extended pursuit. Its teeth also lived brief individual lives. Like living sharks, Cretalamna appendiculata constantly replaced worn or damaged teeth throughout adulthood. New rows developed behind active ones, gradually rotating forward until older teeth dropped away. Entire rows could be renewed several times each year, leaving thousands of fossils scattered across ancient seafloors. Those discarded teeth became an accidental archive, recording evolutionary change with remarkable clarity across 100 million years. One feature, however, remained absent during this early chapter. The cutting edges were smooth instead of serrated. That detail suited the prey available at the time. Fish covered in scales and coated with slippery skin could often be held more effectively by clean edges than by saw-like ones. Marine mammals with thick blubber and resilient hides had not yet entered the oceans, leaving little pressure for a different solution. Much later, as entirely new prey transformed marine ecosystems, the teeth would begin changing alongside them. Each subtle modification reflected the same enduring conversation between predator and prey, written one fossil tooth at a time. The turning point arrived from the sky. Around 66 million years ago, an asteroid, about 6 miles across, struck the region now known as the Yucatan Peninsula. In a single instant, energy beyond ordinary imagination surged through Earth's crust. Rock vaporized, molten debris arced high above the atmosphere, and shock waves raced outward across continents and oceans. The impact itself lasted only moments, yet its consequences unfolded across months, years, and countless generations that followed. Dust and shattered rock spread around the globe, forming a dense veil that greatly reduced sunlight reaching the surface. Photosynthesis weakened across both land and sea. Temperatures dropped as the planet lost much of the warmth sustained by direct solar energy. Ocean chemistry shifted under mounting stress, while rising acidity challenged organisms that depended upon stable marine conditions. The smallest living producers, phytoplankton drifting through sunlit waters, suffered catastrophic losses. Their decline echoed upward through every layer of the food web, because they nourished the tiny creatures that supported nearly everything larger. As those foundations crumbled, entire branches of marine life disappeared. Ammonites vanished forever after flourishing for hundreds of millions of years. Giant marine reptiles that had ruled the seas through much of the Cretaceous, including mosasaurs and plesiosaurs, reached their final chapter. Many immense sea turtles also disappeared from the fossil record, while numerous large predatory fish declined beyond recovery. Scientists estimate that roughly 75% of marine species perished during this global crisis, leaving ecosystems stripped of many familiar inhabitants. The hierarchy that had shaped the oceans dissolved with startling speed. Hunting grounds, once occupied by enormous reptiles, became strangely open. Dominant predators that had seemed permanent proved vulnerable when the web supporting them collapsed. The disappearance of these giants created an ecological landscape unlike anything the oceans had known for millions of years. Habitats remained, currents still flowed, and coastlines endured, though many of the creatures that defined those places had faded away. Among the survivors appeared a familiar pattern of triangular teeth. Fossils reveal that Cretalamna appendiculata crossed the boundary between the Cretaceous and the age that followed. Those teeth continue into younger rock layers with recognizable form, providing direct evidence that the lineage endured while so many celebrated marine hunters disappeared. The shark itself remained relatively modest in size, measuring no more than about 12 feet, yet it succeeded where far larger animals could not. Its endurance reflected flexibility woven into its way of life. A broad geographic range protected populations from depending upon one region alone. Its feeding habits allowed it to exploit whatever prey remained available instead of relying upon a single source of food. The anatomy inherited across millions of years continued functioning within a transformed ocean, proving that survival often favored adaptable designs capable of meeting unfamiliar circumstances. Recovery unfolded gradually. Marine communities rebuilt themselves from scattered survivors, filling empty habitats generation after generation. Every abandoned hunting ground represented possibility waiting for new occupants. Predators entering this recovering world encountered opportunities unavailable to their predecessors, while prey populations also began following new evolutionary paths. The lineage that had endured the greatest marine catastrophe of its age now occupied a planet where entire levels of the food chain stood open. Across the millions of years ahead, descendants would expand into those vacant roles, one careful step at a time, guided by the durable foundation already carried within their teeth and bodies. Recovery rarely restores a world exactly as it was. As marine ecosystems slowly rebuilt after the Great Extinction, new opportunities emerged where familiar rulers had once dominated. Around 60 million years ago, one branch of the surviving shark lineage expanded into that changing landscape with remarkable success. From the enduring foundation established by Cretalamna appendiculata arose Otodus obliquus, a predator that transformed both the scale and influence of its family. Its name reflects one of the most recognizable details preserved in stone. Derived from Greek words meaning tooth and ear, Otodus obliquus refers to the distinctive ear-shaped lobes, known as auricles, located at the base of each tooth. These structures became an important identifying feature for paleontologists studying the earliest members of this expanding lineage. Even after millions of years beneath layers of sediment, the characteristic shape remained clear enough to distinguish these fossils from those of other ancient sharks. Body size changed dramatically as well. Estimates suggest that Otodus obliquus reached roughly 30 feet in length and weighed more than 8 tons. That placed it well beyond the dimensions of the largest living great white shark and established it as the greatest carnivorous fish known from the recovering Paleocene seas. Such growth represented more than an increase in length. Every feature, from its jaws to its swimming muscles, reflected a predator capable of pursuing substantially larger prey across broad stretches of warm ocean. Its fossil record reveals an equally impressive geographic range. Teeth and vertebral centers have been recovered from Morocco, North America, Europe, and Pakistan, demonstrating that this shark occupied many of the shallow tropical and subtropical seas covering parts of the globe during the Paleocene. Those widespread discoveries suggest populations flourished across connected marine environments, traveling through waters rich with fish and other recovering life while maintaining the distinctive characteristics inherited from earlier ancestors. The world surrounding Otodus obliquus differed profoundly from the oceans that had shaped its predecessors. Mosasaurs no longer patrolled coastal waters. Plesiosaurs had disappeared from every sea. The giant marine reptiles that once occupied the highest levels of predation had vanished completely, leaving no comparable successors. An ecological limit that had constrained the evolution of sharks for millions of years had dissolved. For the first time within this family's history, the largest predator in the ocean was no longer a reptile. It was a shark. The seas themselves remained warm and productive as recovery continued. Large bony fish spread through coastal habitats, while primitive sea turtles occupied familiar feeding grounds. Along river mouths and shorelines, the earliest ancestors of whales had only begun their gradual transition from life on land into permanent existence within the sea. Few creatures possessed either the size or weaponry necessary to challenge a healthy adult Otodus obliquus. Its position near the summit of marine predation rested upon both physical power and the absence of former rivals. This achievement marked far more than the arrival of a larger shark. Otodus obliquus entered an ocean still rebuilding from immense ecological loss and established dominance without inheriting an already balanced community of giant predators. It expanded into spaces left empty by extinction, proving that adaptability could eventually give rise to extraordinary size. The dynasty leading toward Megalodon had crossed an important threshold. Its members no longer survived within another predator's shadow. They had become the defining presence of the recovering sea, carrying forward a legacy built through endurance before it was expressed through overwhelming scale. Warm currents connected coastlines that today stand separated by deserts, mountains, and continents. During the Eocene, beginning about 56 million years ago, Earth's oceans entered one of the warmest chapters of the entire Cenozoic era. Tropical sea surface temperatures often approached 95 degrees Fahrenheit, while broad, shallow waters spread across regions that are now the Sahara, southern Europe, and much of the southern United States. Marine life expanded through these welcoming conditions, filling nearly every available habitat with remarkable diversity. Flowing through the heart of this world was the Tethys Sea, an immense body of water stretching from the lands now called Spain across to present-day Pakistan. Its warm, sunlit shallows supported enormous populations of fish, marine reptiles that had newly evolved after earlier extinctions, sea turtles, shellfish, and the earliest marine mammals. Rich coastal shelves blended into deeper channels, creating ideal hunting grounds for predators able to travel great distances in search of food. Few hunters matched the reach of Otodus obliquus across this expansive marine corridor. Some of the clearest windows into that vanished ecosystem lie within the phosphate deposits of Morocco, particularly the Oulad Abdon Basin. For generations, these rocks have yielded thousands of beautifully preserved Otodus obliquus teeth, together with bones from early whales, giant sea turtles, large bony fish, and countless other marine animals. Each fossil emerged from sediments laid down within productive coastal waters where predator and prey repeatedly crossed paths. Instead of preserving isolated discoveries, these deposits record an entire living community assembled across immense spans of time. The menu available to Otodus obliquus reflected that abundance. Large bony fish remained important prey, joined by turtles and early relatives of modern sea cows. Yet another opportunity gradually appeared within the recovering seas. Mammals that had once lived entirely on land began returning to aquatic life, creating a completely new source of food, unlike anything encountered by earlier generations of sharks. Their arrival altered marine ecosystems in subtle ways that would echo through millions of years of evolution. Among these pioneering mammals were the archaeocets, the earliest whales. The oldest forms, including Pakicetus, still spent much of their lives on land despite possessing adaptations that hinted at an aquatic future. Later came Ambulocetus, capable of walking across shorelines while swimming with increasing confidence. More advanced forms, such as Rhodochetus, became even better suited to permanent marine existence, though they still differed greatly from the streamlined whales familiar today. Most measured no larger than sizable seals or small dolphins, carrying traces of their terrestrial ancestry within their limbs and skeletons. This timing gave Otodus obliquus an unusual place in natural history. It hunted whales before whales had completed their transformation into fully marine giants. Its prey represented an evolutionary experiment still unfolding, with each generation becoming better adapted to life in the sea. Predator and prey changed together, each responding to new pressures within an environment that remained rich with opportunity and competition. The shark's anatomy remained well suited to this changing world. Smooth-edged teeth still gripped slippery bodies effectively, while powerful jaws delivered decisive bites during swift upward attacks from below. The strategy inherited from earlier ancestors expanded naturally as prey increased in size and variety. Rather than waiting for stable ecosystems to emerge, Otodus obliquus flourished within an ocean where new forms of life continually appeared, establishing patterns of predation that later descendants would refine across the ages without abandoning their oldest foundations. A change in prey can redirect the course of an entire family of predators. As the earliest whales spread through Eocene seas, Otodus obliquus encountered a source of food unlike anything its ancestors had known. These mammals still carried traces of their terrestrial beginnings, yet they had become regular inhabitants of warm coastal waters. Their arrival introduced a new relationship into marine ecosystems, one that would shape the shark lineage for tens of millions of years. The fossil record preserves remarkable glimpses of these encounters. Teeth belonging to Otodus obliquus have been recovered from the same rock layers that contain archaeocete whale skeletons in Morocco, Pakistan, and Egypt. Such repeated associations across widely separated regions point toward a genuine ecological connection rather than chance burial. Although direct bite marks remain uncommon, the persistent appearance of predator and prey within the same ancient environments strongly supports active hunting instead of simple scavenging after death. These early whales differed greatly from the familiar giants crossing modern oceans. Their bodies reflected an evolutionary transition still underway, combining inherited traits from land-dwelling ancestors with increasingly effective adaptations for aquatic life. Swimming abilities improved from one species to the next, though many retained anatomical features revealing where their story had begun. They occupied an intermediate chapter that existed only briefly in geological time before later whales followed entirely different paths. Among the most fascinating was Myacetus, an animal measuring about 8 feet in length. Strong legs still supported its weight on land, allowing it to move between shorelines and shallow coastal waters. Fossil discoveries suggest it gave birth on land before returning to the sea, preserving one of the clearest records of this remarkable transition. A predator, such as Otodus obliquus, hunted creatures that could still walk, creating one of the most striking combinations preserved within ancient marine ecosystems. Another archaeocete, Basilosaurus, represented a very different stage of whale evolution. Stretching to roughly 60 feet, its long serpentine body moved through warm seas with powerful undulations. Tiny hind limbs remained attached near the rear of the body, serving as reminders of distant terrestrial ancestry while contributing little to swimming. Unlike modern baleen whales, Basilosaurus possessed formidable teeth and hunted other marine animals. It stood among the dominant predators of its own age, sharing waters with Otodus obliquus rather than existing merely as helpless prey. Chemical evidence strengthens this picture. A study published during 2004 by paleontologist Bruce McFadden and colleagues examined stable isotope patterns preserved within Otodus obliquus, teeth collected from Eocene deposits in Morocco. Those chemical signatures revealed a diet unusually rich in marine mammals, differing clearly from sharks feeding primarily upon fish. Because stable isotopes reflect the foods consumed throughout life, they provide independent support for repeated hunting of whale relatives and other marine mammals instead of occasional feeding opportunities. This dietary shift carried lasting consequences. Earlier sharks had certainly consumed marine vertebrates when circumstances allowed, yet no known lineage had reached a combination of body size, jaw design, and feeding strategy capable of relying so heavily upon marine mammals. Otodus obliquus demonstrated that such prey could support a giant shark, establishing an ecological pattern inherited by every major descendant that followed. Through successive generations, the relationship between predator and whale deepened, becoming one of the defining stories written across the fossil record of Earth's changing oceans. Every dominant predator eventually encounters another hunter capable of challenging its place. During the Eocene, Otodus obliquus shared its realm with one of the most formidable marine mammals ever to evolve. This was Basilosaurus, a creature whose long body wound through warm seas with remarkable confidence. It occupied the same coastlines, crossed many of the same hunting grounds, and pursued many of the same prey, creating one of the most extraordinary predator pairings preserved in the fossil record. Despite its name, Basilosaurus was no reptile. Early paleontologists first described its enormous fossil bones before recognizing that they belonged to an ancient whale. The original name, meaning king lizard, reflected that understandable mistake. Later discoveries revealed unmistakable mammalian anatomy, yet scientific naming rules preserved the familiar title. The misleading name survived even as understanding of the animal changed completely, becoming a reminder of how paleontology continually refines its own history. Adult Basilosaurus stretched between roughly 55 and 65 feet in length. Its body resembled an immense sea serpent, flexible and elongated rather than compact like modern whales. Estimates suggest it outweighed Otodus obliquus by perhaps 2 or 3 times, making it one of the largest predators inhabiting Eocene oceans. Tiny hind limbs remained near the rear of its body, no longer useful for walking, yet still present as echoes of distant terrestrial ancestry carried forward through evolution. Its jaws reflected an equally impressive level of specialization. Unlike the smooth-edged teeth carried by Otodus obliquus, Basilosaurus possessed complex teeth equipped for slicing flesh and crushing bone. Fossil discoveries have confirmed the effectiveness of that bite. Juvenile Dorodon skeletons preserve distinctive bite marks matching the tooth pattern of Basilosaurus, evidence examined in a study published during 2019. Those injuries demonstrate repeated attacks by a predator fully capable of overpowering young whales within its environment. Additional confirmation comes from an exceptional fossil recovered at Wadi al-Hitan in Egypt. Preserved stomach contents inside one Basilosaurus specimen include remains of juvenile Dorodon together with large fish. This discovery provided the first direct fossil evidence identifying the feeding behavior of an Eocene whale. Rather than relying solely upon tooth marks or indirect clues, paleontologists could examine the remains of prey carried within the predator itself, offering an unusually complete glimpse into daily life within those vanished seas. That evidence also reveals remarkable overlap with Otodus obliquus. Both predators inhabited much of the same geographic range across the Eocene. Both hunted large fish and early marine mammals. Their fossils occur together in several important localities, demonstrating they belong to the same living communities instead of replacing one another through time. They were neighbors, competing within ecosystems rich enough to sustain multiple giant hunters. One possibility remains unresolved. Some researchers have proposed that Basilosaurus may occasionally have attacked Otodus obliquus. A shark measuring around 30 feet fell within the potential prey size of a whale approaching 60 feet. Fossil ribs attributed to Otodus discovered alongside Basilosaurus remains bear damage that cannot exclude such encounters, though the available evidence remains inconclusive. No specimen yet preserves the decisive proof needed to settle the question. Even without certainty, the broader picture is striking. The Eocene supported two immense apex predators sharing the same waters, often pursuing similar prey while evolving along very different paths. Later oceans ruled by Megalodon never appear to have contained another hunter occupying an equivalent position for so long. Otodus obliquus flourished within a marine world where dominance was continually measured against an equally formidable rival. Evolution often leaves its earliest clues in details so small they could pass unnoticed without careful examination. Around 45 million years ago, paleontologists begin seeing a subtle alteration along the cutting edges of teeth, belonging to the descendants of Otodus obliquus. At first, the change appears almost uncertain, visible only as faint irregular notches interrupting an otherwise smooth edge. Across younger rock layers, those tiny interruptions become more frequent, more orderly, and increasingly precise until the teeth display unmistakable serrations. Nothing about this transformation suggests a sudden leap. Fossils preserve every intermediate stage, allowing researchers to follow the process across immense spans of time. Some teeth remain almost identical to their smooth-edged ancestors. Others carry only scattered projections along portions of the crown. Later examples reveal finely developed serrations extending across the entire cutting margin. The progression unfolds gradually enough that neighboring populations may have displayed different degrees of development while sharing many other physical characteristics. These changing edges reveal an equally important shift in feeding ecology. Smooth teeth perform exceptionally well when gripping slippery fish covered with scales and mucus. Serrations serve a different purpose. Tiny cutting projections concentrate force along the tooth edge, allowing it to slice more effectively through dense muscle, resilient skin, and thick layers of blubber. Marine mammals presented exactly those challenges. As whales became larger and increasingly abundant throughout Eocene seas, predators able to process such prey more efficiently gained an important advantage. In this sense, the teeth recorded changes occurring beyond the shark itself. The fossil record preserves evidence of whales growing more diverse, occupying new ecological roles, and spreading across broad marine habitats. Every improvement in their success created additional opportunities for predators specializing in marine mammals. The evolving shark lineage responded generation after generation, with natural selection favoring individuals whose teeth handled these increasingly substantial prey animals more effectively. Predator and prey advanced together, each influencing the evolutionary direction of the other. Some paleontologists recognize transitional populations from this period as a distinct species called Otodus axuaticus. These sharks retained many features inherited from Otodus obliquus while displaying the earliest consistent development of serrated tooth edges. Their fossils illustrate how difficult it can be to divide evolution into separate categories. Instead of sharp boundaries, the lineage resembles a flowing continuum in which gradual anatomical changes accumulate until descendants become recognizably different from their ancestors. The next widely recognized stage appears with Otodus auriculatus, entering the fossil record roughly between 45 and 40 million years ago. Estimated to reach approximately 25 to 30 feet in length, it remained comparable in overall size to its predecessor. The most significant transformation occurred within the teeth themselves. Serrations became more evident, while the small lateral cusplets, inherited from earlier members of the genus, persisted but began shrinking. Those familiar structures still marked the lineage, though they no longer dominated the outline of each tooth. Beyond the jaws of these sharks, the world itself was changing. Global climates gradually cooled as the Eocene approached its close. The broad Tethys Sea slowly contracted under shifting geography and climate, altering coastlines that had supported countless generations of marine life. Whales continued evolving into more specialized swimmers, and predators evolved beside them. The fossil teeth resting within ancient sediments preserve that shared history with remarkable clarity, revealing that every new edge reflected far more than anatomy alone. It recorded an ocean reshaping itself, one generation after another. Earth does not always transform through sudden catastrophe. Sometimes an age fades little by little until familiar coastlines, currents, and living communities become something entirely different. Around 34 million years ago, the boundary between the Eocene and Oligocene marked one of the most significant climatic transitions of the Cenozoic era. Across the globe, long-established patterns of warmth began giving way to a cooler planetary climate whose influence reached every ocean. Temperatures declined across both land and sea, altering circulation patterns that had remained relatively stable for millions of years. Antarctica, which had previously supported forests during warmer intervals, developed its first major continental ice sheet. Vast quantities of water became locked within expanding ice, causing global sea levels to fall. Broad continental shelves that had once rested beneath shallow tropical seas gradually emerged, while marine habitats contracted along many coastlines. Entire ecosystems adjusted to a world becoming progressively less hospitable to species adapted to prolonged warmth. One of the greatest geographical changes unfolded within the Tethys Sea. For countless generations, it had linked distant regions through warm marine corridors stretching across much of the ancient world. As the African tectonic plate continued its slow movement northward, those waters narrowed into separated basins. The familiar Mediterranean Sea had not yet formed. Instead, the once continuous Tethys fragmented, leaving isolated marine environments where broad expanses of open water had previously supported thriving communities of predators and prey. Such environmental change inevitably reached the animals living within those seas. Many Archaeocete whales, already specialized for conditions that had dominated the Eocene, struggled as coastlines shifted and habitats disappeared. Several lineages eventually vanished from the fossil record. Their disappearance did not leave the oceans empty, however. Other whales followed different evolutionary paths, giving rise to groups whose descendants still inhabit modern seas. The earliest baleen whales and the first toothed whales appeared during this period, introducing fresh forms into ecosystems undergoing widespread reorganization. These newcomers remained modest compared with the enormous whales familiar today. Even so, they represented an important ecological transition. Baleen feeding opened possibilities for exploiting abundant microscopic life suspended within seawater, while toothed whales diversified into active hunters using increasingly specialized senses and behaviors. The marine mammal community became more varied than before, providing opportunities for predators capable of adapting alongside their changing prey. Every evolutionary advance among whales reshaped the resources available to the shark lineage that had followed them for millions of years. The family descending from Otodus obliquus had already endured extraordinary challenges. Earlier ancestors survived the Cretaceous-Paleogene extinction, persisting through the collapse of marine food webs that eliminated countless dominant species. Later generations crossed intervals of exceptional warmth before entering this prolonged cooling episode. Each environmental shift tested their flexibility, yet the lineage continued changing instead of disappearing. Its evolutionary design proved capable of responding to different oceans without abandoning the core adaptations that had carried it this far. That resilience often receives far less attention than sheer size. Enormous teeth naturally capture imagination, while survival across repeated planetary upheavals attracts less notice despite requiring equally remarkable biological success. Extinction favored neither the strongest nor the largest with complete consistency. Populations capable of adjusting to altered coastlines, shifting prey communities, and changing climates often endured where seemingly invincible rulers disappeared. The history of this shark family illustrates that principle with unusual clarity. As cooler oceans settled into their new balance, another inheritance took shape. Future descendants would enter seas occupied by increasingly modern whales, many growing larger with each passing age. Their ancestors had already weathered transformations that reshaped continents and climates alike. Those earlier victories did not guarantee permanent success, yet they revealed a lineage built upon persistence across changing worlds, as much as upon the formidable teeth that first drew scientific attention. Time continued its patient work upon the lineage, shaping each generation with small adjustments that accumulated across millions of years. By the beginning of the Oligocene, roughly 33 million years ago, another successor had emerged from that long evolutionary current. Paleontologists know it as Otodus angustidens, whose name means narrow ear tooth. It carried the familiar heritage of its ancestors, while displaying anatomical refinements that drew the family another step toward the predator history would eventually recognize as Megalodon. Body size increased once again. Most estimates place mature Otodus angustidens between 30 and 35 feet in length, although exceptionally large specimens suggest that certain individuals may have approached 40 feet. Even without reaching the greatest dimensions achieved by its famous descendant, it represented the largest member of the lineage known up to that point. Greater mass allowed it to pursue larger prey while maintaining the swimming power necessary for long journeys through expanding marine habitats. Its teeth reveal perhaps the clearest evidence of continuing specialization. Individual crowns could reach nearly 4 inches in length, with fully developed serrations extending along both cutting edges. The small lateral cusplets inherited from earlier ancestors remained present, although they had become noticeably reduced. Viewed beside the teeth of Otodus obliquus, the evolutionary direction becomes unmistakable. The broad cutting blade now dominated the crown, moving steadily toward the clean triangular form that later generations would perfect. Those sharpened edges left traces upon the fossil record. At the Doberg locality in Germany, ribs belonging to ancient sea cows preserve bite marks matching the distinctive shape and spacing of Otodus angustidens teeth. Similar evidence appears within early baleen whale fossils recovered from the Charleston embayment of present-day South Carolina. These wounds provide direct physical evidence linking the shark to attacks upon large marine mammals, extending the ecological pattern established by its predecessors into an increasingly whale-rich ocean. Biomechanical studies help explain why these teeth proved so effective. Their design favored slicing instead of crushing. During an attack, a powerful sideways motion of the jaws allowed the serrated edges to cut deeply through skin, blubber, and muscle while producing extensive blood loss. Such anatomy suggests an ambush strategy focused upon inflicting severe wounds before allowing weakened prey to succumb. Every aspect of the tooth reflected efficiency against large, soft-bodied animals rather than repeated impacts against heavy bone. The expanding diversity of marine mammals provided abundant opportunities for such a hunter. Early baleen whales had become increasingly common, although they remained much smaller than the enormous species inhabiting modern oceans. Dolphins, sea cows, sea turtles, and large fish also formed part of the available prey community. Instead of relying upon a single food source, Otodus angustidens occupied the highest feeding levels within ecosystems containing many substantial marine vertebrates, allowing flexibility as local conditions changed. Chemical evidence reinforces that interpretation. Nitrogen isotope patterns preserved within fossil tooth enamel consistently place Otodus angustidens above predators, feeding mainly upon fish. Such elevated isotope values indicate regular consumption of animals already occupying high positions within marine food webs, especially marine mammals. These chemical signatures align closely with the physical evidence left upon fossil skeletons, strengthening the picture of an apex predator regularly hunting other dominant vertebrates. Growth likely influenced diet as well. Smaller juveniles probably captured fish and other modest prey, better suited to their developing bodies. As individuals matured and their jaws expanded, increasingly large marine mammals became practical targets. This progression from youthful fish hunting to adult whale predation appears remarkably familiar. Long before Megalodon inherited that strategy, Otodus angustidens had already demonstrated how one shark lineage could transform alongside its own growth, matching every stage of life to a different place within the ocean's living tapestry. No ocean remains dominated by a single hunter forever. As the Oligocene progressed, the shark lineage encountered another expanding branch of marine predators, one descended from mammals instead of fishes. These newcomers belonged to the toothed whales, animals whose intelligence, powerful jaws, and active hunting behavior gradually established them among the highest levels of marine food webs. Their arrival marked another turning point in the long history of competition across the sea. One of the clearest later examples comes from Zygophysiter veroli, a macroraptorial sperm whale that lived much later during the Miocene. Measuring more than 20 feet in length, it carried enormous serrated teeth in both upper and lower jaws, unlike the modern sperm whale, whose functional teeth are largely confined to the lower jaw. Finite element analysis, published during 2021, demonstrated that its skull and jaws could withstand the tremendous forces required to seize struggling prey and even crack whalebone. Although separated from Otodus angustidens by millions of years, Zygophysiter illustrates the ecological direction that predatory sperm whales eventually followed. The Oligocene already contained earlier representatives moving toward that same lifestyle. Primitive toothed whales diversified rapidly after the disappearance of older Archaeocete lineages, experimenting with new hunting strategies as marine mammal communities expanded. They had not yet reached the extreme specializations seen in later macroaptorial sperm whales, yet they occupied increasingly similar ecological roles. They pursued large prey, relied upon formidable teeth instead of baleen, and entered coastal ecosystems already patrolled by giant sharks. That overlap created one of the most demanding environments the lineage had experienced since the days when Otodus obliquus shared warm seas with Basilosaurus. Giant sharks and predatory toothed whales hunted many of the same marine mammals, following comparable migration routes and exploiting the same productive feeding grounds. Neither lineage represented a temporary visitor. Both became established components of Oligocene ecosystems, each refining different anatomical solutions to the challenge of capturing large vertebrate prey. Unlike later intervals when Megalodon possessed an overwhelming advantage in body size, the Oligocene supported several predators occupying broadly comparable positions within marine food webs. Large sharks remained extraordinarily capable hunters, yet they no longer existed without meaningful competition from other apex carnivores. Coastal waters became arenas where multiple hunting strategies operated simultaneously. Speed, endurance, jaw structure, sensory abilities, and prey selection all contributed to survival within communities growing steadily more complex. Fossils reinforce this picture of coexistence. Deposits from the Charleston embayment of present-day South Carolina preserve Otodus angustidens teeth alongside remains of early toothed whales, indicating that both inhabited the same coastal environments. Similar associations appear within the fossil-rich sediments of the Oiled Abdun Basin in Morocco, where shark teeth occur among diverse marine mammal remains. Although fossils rarely capture direct encounters between rival predators, they demonstrate repeated occupation of the same habitats across long stretches of geological time. Competition did not halt the lineage's progress. Throughout its history, this family repeatedly answered environmental pressure through gradual evolutionary refinement. Teeth became more efficient cutting tools. Body size continued increasing. Dependence upon marine mammals deepened as whales themselves diversified. Every challenge reshaped the predator without breaking it. The presence of powerful toothed whales added another force guiding that transformation, encouraging continued specialization within a lineage that had already endured dramatic climatic shifts, changing oceans, and successive generations of formidable rivals while steadily advancing toward its greatest expression. Every fossil carries more information than its appearance first suggests. A single tooth, a damaged rib, or a weathered vertebra can preserve evidence of lives that ended tens of millions of years ago. Paleontologists approach these remains much like forensic investigators, assembling countless small observations into a coherent picture of vanished ecosystems. The ancestors of Megalodon have become increasingly well understood through this careful process, where conclusions emerge from measurable physical evidence rather than imagination. Among the strongest clues are bite marks preserved on fossil bones. Each shark species produced teeth with distinctive shapes, serration patterns, crown widths, and spacing. When those teeth sliced into bone, they sometimes left impressions matching the anatomy of the jaws that created them. Researchers examine the width, curvature, depth, and microscopic details of these marks, comparing them directly with fossil teeth. Ribs from marine mammals bearing wounds attributed to Otodus angustidens preserve serrated impressions consistent with its characteristic cutting edges, allowing scientists to identify the predator with considerable confidence. Chemical evidence offers another independent source of information. Nitrogen isotopes become progressively enriched at higher positions within a food web, allowing researchers to estimate an animal's trophic level from preserved tissues. During the last decade, advances in enameloid-bound nitrogen analysis made it possible to apply this technique reliably to fossil shark teeth. Because tooth enamel preserves chemical signatures exceptionally well, scientists can compare ancient sharks with one another and determine whether their diets centered upon fish, marine mammals, or other prey occupying different ecological positions. Those chemical results consistently reinforce conclusions drawn from anatomy. Sharks occupying the highest trophic levels display greater enrichment in nitrogen isotopes than predators feeding lower in the food chain. Members of the Otodus lineage repeatedly fall among the highest values measured within their ecosystems, supporting the interpretation that large marine mammals formed a substantial portion of their diet. Independent methods arriving at similar conclusions strengthen confidence that these reconstructions reflect genuine biological patterns instead of isolated observations. The surrounding rocks contribute important evidence as well. Fossils rarely occur alone. Teeth, bones, shells, and sediments preserve the broader community existing at the time of burial. When shark teeth repeatedly appear within the same geological layer, embedded in the same matrix, and associated with particular marine mammal remains, scientists can reconstruct ecological relationships extending beyond individual specimens. Morocco's phosphate deposits provide remarkable examples of this preservation, recording Eocene marine ecosystems with extraordinary richness. Predators and prey remain linked within the same ancient sediments, offering an unusually detailed record of community structure. Growth patterns also survive inside shark vertebrae. Much like the annual rings of a tree, vertebral centra accumulate concentric growth bands throughout life. Counting those bands allows researchers to estimate age, growth rate, and maturity at death. One exceptionally preserved Otodus angustidens specimen from New Zealand includes 35 associated vertebral centra, providing valuable information about development across the animal's lifetime. Such discoveries reveal how quickly these sharks grew and help estimate the sizes reached at different ages. Even with such evidence, important limits remain. Teeth cannot reveal body coloration. Fossils rarely preserve behavior in direct detail. Hunting tactics, social interactions, and migration patterns must be inferred through anatomy, ecological context, and comparisons with living sharks and whales. Those interpretations remain grounded in evidence, though they always carry appropriate scientific caution. That balance between certainty and inference gives this lineage its remarkable clarity. Whale hunting, competition with other apex predators, and progressive evolutionary change are supported by fossil teeth, bite marks, isotope chemistry, associated skeletons, and vertebral growth records gathered across many continents. Each line of evidence strengthens the others, creating a history built from physical traces that have endured across millions of years. Some evolutionary changes transform an entire lineage without altering the overall shape of the animal. Across nearly 40 million years, the ancestors of Megalodon carried the same basic body plan through changing oceans. Yet one feature continued to evolve with remarkable consistency. The cutting edge of the tooth became progressively more sophisticated, recording an unbroken history of adaptation preserved in stone. Few anatomical structures reveal such a continuous sequence of refinement from one species to the next. The story begins with Cretalamna. Its teeth possessed smooth cutting edges well suited for grasping fast-moving fish. Slippery prey required secure penetration more than slicing ability, and the simple crown accomplished that task efficiently. Millions of years later, Otodus obliquus inherited essentially the same design. Most individuals still carried completely smooth teeth, although later populations began displaying faint irregular notches along portions of the cutting edge. Those tiny variations hinted that natural selection was beginning to favor a different approach. The next stage appeared in Otodus auriculatus. Serrations became visible across much of the tooth, although their development remained inconsistent from one individual to another. Some specimens retained relatively simple edges, while others displayed much finer cutting structures. Evolution rarely advances in perfectly uniform steps, and this species illustrates that gradual process clearly. Populations contained a range of tooth forms, reflecting natural variation as the lineage continued adjusting to changing ecological conditions. By the time Otodus angustidens emerged, that uncertainty had largely disappeared. Its teeth carried fully developed serrations, extending along both cutting margins with remarkable regularity. The pattern became finer, more evenly spaced, and better suited for slicing substantial prey. Small lateral cusplets still remained near the base of the crown, preserving a visible connection to earlier ancestors even as their importance steadily declined. The cutting blade itself had become the defining feature. Further refinement continued with Otodus chubutensis. Serrations achieved an even more consistent appearance, while the lateral cusplets shrank until they approached disappearance. The crown assumed an increasingly simple, triangular outline dedicated almost entirely to cutting performance. Every reduction of unnecessary structure concentrated functional emphasis upon the main blade, preparing the lineage for its final and most specialized expression. That culmination arrived with Otodus megalodon. The familiar triangular tooth displayed no remaining lateral cusplets, only an immense cutting surface bordered by precise serrations. Paleontologists regard this design as one of the most efficient slicing teeth produced during shark evolution. Its effectiveness did not arise from greater size alone. Millions of years of gradual modification had refined nearly every aspect of the cutting edge, creating a tool uniquely suited to processing enormous marine mammals. The force driving these changes came from the prey itself. Early fish required secure gripping, yet increasingly large whales presented a different mechanical challenge. Thick blubber, resilient skin, and dense muscle responded more effectively to repeated slicing than to simple puncture. Serrations functioned much like the teeth of a saw. During a sideways pull of the jaws, each tiny projection concentrated force into numerous small contact points, allowing deep cuts with less overall effort than a smooth blade demanded. One of the most intriguing patterns within this lineage is that serrations became finer as body size increased. Intuition might suggest larger predators would depend primarily upon greater strength, producing broader or rougher cutting edges. The fossil record shows the opposite. Larger species evolved increasingly delicate, regular serrations that improved efficiency instead of relying upon brute force. Better teeth supported larger prey favored larger sharks, and each evolutionary advance reinforced the next. Across 40 million years, one anatomical innovation became tightly linked with ecological success, leaving a continuous record unmatched by almost any other vertebrate predator lineage. There are moments in evolution when one species seems to stand with a foot in two different worlds. Around 28 million years ago, during the Miocene, the shark lineage reached such a point. Paleontologists recognize this remarkable predator as Otodus chubutensis, named after Argentina's Chubut province, where especially important fossil specimens help define the species. It occupied a place so close to Megalodon that separating the two often becomes an exercise in studying the smallest anatomical details. Its size reflected that close relationship. Large individuals are estimated to have reached between 30 and 40 feet in length, placing them comfortably within the lower range proposed for Megalodon itself. Such overlap has led some researchers to question whether Otodus chubutensis and Megalodon truly represent separate species or whether they form successive stages within a single evolving chronospecies. Under that interpretation, one gradually transformed into the other through continuous evolutionary change instead of an abrupt biological replacement. The teeth preserve the strongest evidence for distinguishing them. At first glance, a large Otodus chubutensis tooth appears remarkably similar to that of Megalodon. It displays a broad triangular crown bordered by finely developed serrations extending along both cutting edges. Only close examination reveals the lingering signature of its ancestry. Tiny residual cusplets remain near the base of the crown, greatly reduced yet still present. They resemble a faint echo carried forward from the earliest members of the lineage, surviving almost 75 million years after their ancestors first displayed them prominently. Those diminishing structures demonstrate how gradually evolution often proceeds. Features seldom vanish all at once. Instead, they shrink generation after generation until their original function fades into history. Within Otodus chubutensis, the ancestral design had nearly completed its transformation. The familiar triangular blade dominated the tooth, while the remaining cusplets persisted almost as historical records embedded within living anatomy. Soon, even those traces would disappear. Fossils reveal that this predator ranged across an immense portion of the world's oceans. Teeth and skeletal remains have been recovered from Argentina, Peru, North America, Europe, Africa, and New Zealand. Such broad geographic distribution indicates exceptional ecological success across many different marine environments. Wherever productive coastal waters supported abundant marine mammals, Otodus chubutensis found opportunities to thrive. Few members of the lineage achieved such a widespread presence before or afterward. The oceans themselves had changed substantially since the cooling that reshaped the late Eocene. During much of the Miocene, warmer conditions returned across many regions, encouraging the expansion of diverse marine ecosystems. Baleen whales completed much of their early evolutionary radiation, filling oceans with an unprecedented variety of species. Some had already reached impressive lengths, approaching 30 or 40 feet, providing prey far larger than anything available to earlier ancestors. Marine productivity supported increasingly complex food webs extending from microscopic plankton to gigantic vertebrates. Alongside these whales appeared additional prey unavailable to previous generations. Pinnipeds, including the earliest seals and sea lions, became regular inhabitants of coastal environments during the early Miocene. Dolphins diversified into numerous forms, while large fish continued occupying productive waters. Such abundance allowed an enormous predator to exploit multiple food sources while remaining closely tied to marine mammals that had become central to the family's ecological identity. Viewed across the entire lineage, Otodus chubutensis represents refinement approaching completion. Body size, tooth design, hunting specialization, and worldwide distribution all stood near their highest levels. The remaining distinction, separating it from Megalodon, rested mainly in degree instead of direction. Slightly larger teeth, a somewhat greater body, and the final disappearance of those lingering cusplets would complete an evolutionary journey that had begun with smooth-edged fish hunters tens of millions of years before, advancing through countless small changes toward its most specialized expression. Evolution is often remembered through its triumphs, yet the fossil record tells a more uncertain story. Even the lineage that would eventually produce Megalodon passed through intervals when its future appeared increasingly fragile. Across millions of years, populations contracted, habitats shifted, and familiar coastlines disappeared beneath changing climates. Survival depended upon enduring these interruptions, each one narrowing the path that stretched from early ancestors toward their greatest descendant. The first major challenge arrived during the transition between the Eocene and Oligocene. Global cooling altered ocean circulation, lowered sea levels, and reorganized marine communities. Those environmental changes affected the distribution of marine mammals that had become increasingly important to the shark lineage. Fossil evidence reveals that the transition from Otodus auriculatus to Otodus angustidens is incomplete across several regions of the world. In some ocean basins, the record contains intervals where members of the lineage appear to vanish entirely before reappearing in younger sediments. Such gaps do not necessarily indicate complete extinction, yet they strongly suggest substantial regional declines or migrations away from environments where fossils were later preserved. These interruptions remind paleontologists that geological history is always incomplete. Sediments accumulate unevenly, coastlines shift, and erosion removes chapters from Earth's archive. Even so, when comparable absences occur across multiple localities, they point toward genuine ecological stress affecting broad populations. The lineage persisted, though its distribution almost certainly became more restricted than during periods of greater environmental stability. Millions of years later, another challenge emerged during the Middle Miocene climate transition, beginning around 14 million years ago. Global temperatures declined once more, and expanding Antarctic ice altered sea levels and ocean circulation. Warm marine habitats contracted across portions of the world, reducing the environments favored by many large marine vertebrates. Within several fossil deposits, researchers have observed a noticeable decline in the abundance of Otodus chubutensis specimens during this interval. Although preservation biases always require careful consideration, the pattern aligns with broader environmental changes recorded in marine sediments. Climate alone did not create the greatest difficulty. The geography of reproduction introduced another vulnerability. Evidence from coastal fossil deposits containing numerous juvenile teeth suggests that members of this lineage relied upon warm, shallow waters as nursery grounds where young sharks could develop before moving into open marine environments. Such coastal habitats offered food, relatively protected conditions, and suitable temperatures during the earliest stages of life. Whenever falling sea levels or climatic shifts reduced these nursery areas, successful reproduction likely became more difficult across affected regions. A population can withstand losses among adults more readily than interruptions to its youngest generation. Nursery habitats therefore represented a vital foundation supporting every subsequent stage of the life cycle. Their disappearance would have influenced not only local communities, but also the long term resilience of the lineage itself. One characteristic repeatedly prevented these pressures from becoming final. Members of the lineage occupied an extraordinary geographic range, extending across nearly every major ocean. Fossils recovered from widely separated continents demonstrate that populations existed in many different marine ecosystems simultaneously. When environmental conditions deteriorated within one region, other populations continued elsewhere under more favorable circumstances. Geographic breadth acted as a biological safeguard, preserving evolutionary continuity even while individual ocean basins experienced severe ecological change. Viewed across this long history, a striking irony emerges. Dependence upon warm coastal nurseries nearly undermined the lineage on more than one occasion, yet earlier species remained small enough and flexible enough to persist through repeated environmental disruption. Their descendants inherited that same ecological preference while growing ever larger and increasingly specialized. The very adaptation that supported millions of years of success carried an enduring vulnerability from one generation to the next, woven through the lineage long before its final chapter was written. Around 23 million years ago, the long evolutionary path finally reached its most recognizable destination. During the early Miocene, Otodus megalodon appeared in the fossil record, most likely evolving from populations of Otodus chubutensis. The transition was subtle rather than abrupt. The familiar triangular tooth remained, yet one final ancestral feature disappeared. The small lateral cusplets that had persisted through earlier species were finally gone, leaving a broad, uninterrupted cutting blade. After tens of millions of years of gradual refinement, the lineage had reached its terminal form. The earliest megalodon was already an immense predator. Fossils from the oldest Miocene deposits indicate adults commonly reached between 45 and 50 feet in length. That placed even early individuals beyond the size of any confirmed ancestor. Evolution had not produced a slightly larger version of the previous species. It had produced a shark capable of exploiting ecological opportunities that earlier members of the lineage could only approach. Its appearance reflected the accumulation of countless small adaptations that had steadily increased body size across successive generations. Its teeth displayed those changes with exceptional clarity. The largest known examples approached 7 inches in height, making them among the largest shark teeth ever discovered. A modern great white shark, by comparison, reaches only about 2 inches in its largest teeth. Megalodon's teeth were broad, triangular, and lined with finely developed serrations from base to tip. Every edge functioned as an efficient cutting surface, capable of slicing through thick skin, dense muscle, and heavy layers of blubber with remarkable effectiveness. The jaws carrying those teeth expanded to extraordinary proportions. Reconstructions based upon complete tooth sets and body proportions estimate that a large adult possessed a jaw circumference exceeding 12 feet. Multiple rows of replacement teeth ensured that damaged teeth were continually replaced throughout life. This arrangement allowed the shark to maintain an effective cutting bite despite constant wear from attacking enormous prey. From the beginning of its history, Megalodon occupied warm oceans across nearly the entire planet. Fossils have been recovered from North America, South America, Europe, Africa, Asia, Australia, New Zealand, and many tropical islands. No earlier member of the lineage achieved such extensive worldwide distribution. Wherever warm marine environments supported abundant marine mammals, Megalodon established itself as a dominant predator. Those oceans offered an exceptional abundance of food. Baleen whales had diversified into dozens of species, occupying coastal waters and the open sea. Some approached the size of large modern whales, while many medium-sized species flourished across productive marine habitats. This rich prey community did not emerge alongside Megalodon by coincidence. Its ancestors had spent nearly 80 million years adapting to progressively larger marine mammals, gradually refining tooth shape, body size, and hunting ability until predator and prey became closely matched through evolution. The fossil record also preserves evidence of Megalodon's earliest years. Dense concentrations of juvenile teeth discovered in the Gatun Formation of Panama, the Calvert Cliffs of Maryland, and coastal deposits in Morocco indicate that warm, shallow waters served as nursery grounds. Young sharks likely remained within these protected environments until they grew large enough to venture into deeper offshore habitats where enormous prey awaited. Its appetite matched its extraordinary dimensions. Body size modeling suggests an adult megalodon possessed a stomach capable of holding roughly 10,000 liters of food, approximately the volume of an entire orca whale. Sustaining such a massive predator probably required thousands of pounds of prey every week. That immense demand represented the final outcome of a lineage that had spent millions of years increasing its size, perfecting its teeth, expanding across the world's warm oceans, and evolving alongside the great whales that defined the Miocene seas. An apex predator is defined as much by the absence of competitors as by its own abilities. By the late Miocene, the long evolutionary journey of this shark lineage had reached an ecological position unlike any it had occupied before. Megalodon no longer shared its environment with another predator capable of consistently matching its size, strength, or influence. Earlier ancestors had always lived within crowded worlds where survival demanded constant awareness of equally formidable hunters. Megalodon inherited something different, an ocean where the highest place in the food web belonged almost entirely to itself. That distinction becomes clearer when viewed against the history that came before. Cretalamna entered seas dominated by enormous mosasaurs, marine reptiles powerful enough to prey upon large sharks. Much later, Otodus obliquus occupied waters where the giant whale Basilosaurus hunted as another dominant carnivore. During the age of Otodus angustidens, large raptorial whales expanded into similar ecological roles, creating competition among predators approaching comparable size. Every evolutionary step unfolded in an environment where another hunter could challenge access to prey or even threaten survival. Only one known marine predator approached Megalodon's extraordinary scale. Livyatan melvillei, a giant raptorial sperm whale, possessed interlocking teeth measuring nearly 14 inches in length. Adults are estimated to have reached between 40 and 57 feet, placing them within the same remarkable size range as Megalodon. Both specialized in hunting large marine mammals, making ecological overlap almost certain. Although direct encounters remain unknown, each represented the highest level of predatory evolution achieved within its own branch of the mammalian and shark lineages. The balance shifted once Livyatan melvillei disappeared. Its extinction occurred well before Megalodon reached the final chapters of its own history. From that point onward, no confirmed marine predator occupied an equivalent ecological position. Across warm oceans, Megalodon stood alone at the summit of the food web, facing little meaningful competition from any other carnivore approaching its immense proportions. The structure of the Miocene ecosystem reflected this dominance. Giant baleen whales formed the principal source of large prey, supported by productive oceans rich in smaller fish and plankton. Marine mammals occupied many levels of the ecosystem, while countless smaller predators fed beneath them. Above all of these stood Megalodon. Compared with the ecosystems inhabited by its ancestors, the food web had become more vertically organized, with an exceptionally large predator occupying the highest position and an abundant population of enormous whales supporting its existence. Its physical abilities matched that ecological role. Biomechanical studies estimate that the largest individuals could generate bite forces approaching 40,000 pounds, the greatest calculated for any known animal in Earth's history. A modern great white shark produces roughly 4,000 pounds of bite force, while a large saltwater crocodile reaches approximately 3,700 pounds. Megalodon's jaws exceeded both by an extraordinary margin, combining tremendous force with immense serrated teeth perfected through millions of years of gradual refinement. Fossil whale skeletons preserve clues to how those jaws were used. Bite marks frequently appear around the fins and tail rather than across the center of the body. Damaging these structures would have reduced a whale's ability to swim efficiently before the predator delivered a fatal attack. This strategy reflects the continuation of hunting behaviors that had gradually developed across the lineage since Otodus obliquus first adapted to pursuing early whales. There is an unexpected irony within this remarkable success. Megalodon occupied the least competitive ocean its ancestors had ever known. The dominance it achieved rested upon adaptations forged through nearly 80 million years of repeated challenges, ecological uncertainty, and relentless evolutionary refinement. By the time true supremacy arrived, the hardest struggles already belonged to the distant past. Success can become its own constraint. After millions of years of steady refinement, Megalodon possessed an anatomy that matched its environment with extraordinary precision. Every improvement, from its immense body to its powerful jaws, had increased its effectiveness as a hunter. Yet evolution does not prepare organisms for every possible future. It shapes them for the conditions that exist at a particular moment. By becoming perfectly suited to the Miocene seas, Megalodon also became increasingly dependent upon them. Its immense size carried the greatest cost. Earlier members of the lineage could exploit a broad variety of prey whenever local conditions changed. Megalodon no longer enjoyed that flexibility. A fully grown adult required an enormous and dependable source of food. Body size models suggest that maintaining such a predator demanded tens of thousands of pounds of prey over the course of a single week. Small fish or modest marine mammals could never satisfy those energetic requirements for long. Giant baleen whales had become the foundation upon which its entire existence rested. If those whales declined, the food available to the largest sharks declined with them. This represented a profound shift from the lineage's earliest history. Cretalamna, measuring roughly 12 feet, could consume fish, smaller sharks, marine reptiles, and countless other animals occupying different habitats. Its diet remained flexible because its energy demands remained comparatively modest. Otodus obliquus expanded into larger prey while still retaining opportunities across a wide ecological spectrum. Even after surviving major environmental disruption, it continued adapting to changing marine communities. As body size increased through later species, dietary breadth gradually narrowed while dependence upon marine mammals steadily increased. Temperature introduced another important limitation. Fossil evidence consistently places Megalodon within warm marine environments, while its teeth remain absent from high latitude deposits representing cold ocean conditions. This pattern suggests the species depended upon relatively warm waters throughout its life. Modern great white sharks possess a degree of regional body temperature regulation that allows them to hunt across a much broader range of ocean temperatures. Current evidence indicates Megalodon lacked that level of thermal flexibility, remaining closely tied to waters warmer than approximately 59 degrees Fahrenheit. As climates shifted, suitable habitat would have contracted alongside the warm seas upon which it depended. Its reproductive strategy added another layer of vulnerability. Juvenile teeth recovered from protected coastal deposits indicate that Megalodon relied upon warm, shallow nursery areas where young sharks could grow before entering deeper waters. These coastal environments offered abundant food and reduced danger during the earliest stages of life. They also ranked among the marine habitats most sensitive to falling sea levels and declining temperatures. A reduction in these nursery grounds would have affected each new generation long before adults experienced the full consequences. The pattern becomes striking when viewed across the entire lineage. Smaller ancestors survived by remaining adaptable. They shifted prey, occupied diverse environments, and endured repeated environmental upheavals across tens of millions of years. Megalodon represented the opposite end of that evolutionary progression. At lengths approaching 50 or even 60 feet, it excelled within one particular ecological role more completely than any predecessor. That excellence came with diminishing flexibility. There is a deep irony woven through this history. The lineage achieved its greatness by adapting again and again to changing oceans, changing climates, and changing prey. Megalodon stood as the finest expression of that long process, yet its extraordinary specialization gradually replaced versatility with dependence. The qualities that elevated it above every ancestor also narrowed the range of conditions under which it could continue to thrive. In reaching the highest point of its evolutionary journey, the lineage surrendered much of the resilience that had carried it there for nearly 100 million years. No predator, regardless of its power, can escape a changing planet. Around 5 million years ago, the oceans that had supported Megalodon through countless generations began entering a new chapter. The transformation did not arrive as a single catastrophic event. It unfolded gradually across thousands of lifetimes, altering temperatures, coastlines, currents, and the distribution of life itself. Changes that seemed modest within one generation accumulated into an entirely different world across geological time. Global oceans entered a prolonged period of cooling during the transition from the late Miocene into the early Pliocene. Warm seas that had stretched across broad regions slowly became less extensive as Earth's climate shifted. Polar ice sheets expanded, storing increasing amounts of water as ice. Sea levels gradually fell, exposing continental shelves that had remained submerged for millions of years. Many shallow coastal environments became smaller or disappeared altogether, removing habitats that had supported complex marine communities across warm continental margins. Another profound change followed as North America and South America became fully connected. The closure of the Central American Seaway interrupted ocean circulation patterns that had linked the Atlantic and Pacific Oceans for millions of years. Warm currents that once distributed heat and nutrients across tropical seas changed direction, reshaping marine ecosystems on a global scale. Productive waters that had sustained enormous populations of marine life no longer functioned in quite the same way, and food webs slowly adjusted to these altered conditions. The consequences reached the giant whales that formed the foundation of Megalodon's existence. Many of the slower coastal baleen whale species that had flourished during the Miocene declined as habitats shifted and ocean productivity changed. Studies of marine fossil communities indicate that roughly one-third of large marine megafauna disappeared during this interval. The losses extended across multiple branches of ocean life, but the impact upon large whales carried particular importance for the largest shark ever to live. Each disappearing whale species represented another portion of its dependable food supply slipping away. The whale lineage itself did not vanish. Those that endured increasingly displayed characteristics suited to the changing oceans. Faster swimming, deeper diving, and greater tolerance for colder waters improved their chances of survival as marine environments transformed. These same adaptations also reduced their vulnerability to a predator built for pursuing large animals in comparatively warm coastal regions. The balance that had favored Megalodon through much of the Miocene gradually shifted toward prey that occupied habitats becoming more difficult for it to exploit. Evidence preserved in fossil deposits records this retreat with remarkable consistency. Megalodon teeth disappear first from higher latitude regions, then vanish progressively closer to the equator as colder waters expanded. The pattern resembles a shrinking map, each missing fossil marking another coastline where the species no longer persisted. Its range contracted toward tropical seas that still provided conditions suitable for survival, although those remaining refuges continued to diminish over time. The greatest burden came from the shark's own success. An animal requiring enormous quantities of food could not easily endure prolonged shortages. Earlier members of the lineage had responded to environmental disruption by broadening diets, shifting into new habitats, or gradually evolving different body sizes across many generations. Megalodon's immense scale slowed every one of those possibilities. Adaptation could no longer keep pace with the changing world surrounding it. The final confirmed megalodon teeth date to approximately 3.6 million years ago. Statistical studies of the fossil record suggest extinction may have occurred slightly earlier, near 3.5 million years ago. By then, the cooling oceans had completed a transformation that even the greatest predator of its lineage could not overcome. A family history is often measured by the hardships its members endure. Across nearly 100 million years, the lineage that eventually produced Megalodon encountered disasters capable of reshaping the entire planet. Continents shifted, oceans cooled, prey vanished, and dominant species disappeared. Again and again, these sharks endured. Their survival was never guaranteed, yet each ancestor possessed a flexibility that allowed the lineage to continue. The final chapter stands apart because the qualities that once preserved the family had gradually been replaced by extraordinary specialization. The earliest known representative, Cretalamna, lived through the Cretaceous-Paleogene extinction, the greatest biological crisis ever faced by complex marine ecosystems. The asteroid impact erased marine reptiles, ammonites, and countless other forms of life. Food webs collapsed across the world's oceans. Cretalamna survived because it demanded relatively little from its environment. Measuring roughly 12 feet in length, it hunted a wide assortment of prey, occupied broad geographic ranges, and adapted to whatever food remained after the catastrophe. Versatility became its greatest evolutionary advantage. Millions of years later, Otodus obliquus confronted another planetary transition as global climates cooled during the late Eocene and the Eocene-Oligocene transition. Ocean temperatures declined, ecosystems reorganized, and marine communities shifted into unfamiliar forms. Rather than depending upon one particular source of food, this shark hunted fish alongside the newly evolving whales, beginning to appear across ancient seas. That broad feeding strategy allowed populations to persist while many marine species adjusted to changing climates and coastlines. The next major challenge arrived during the age of Otodus angustidens. Earlier Archaeocete whales that had dominated previous oceans gradually disappeared, replaced by expanding groups of baleen whales and toothed whales. Instead of declining alongside its familiar prey, Otodus angustidens redirected its hunting toward these emerging mammals. Evolution had not produced a rigid specialist. It had produced a predator capable of following opportunity wherever it appeared. Each successful transition strengthened the lineage across millions of additional years. Viewed together, these chapters reveal an extraordinary pattern. Asteroid impacts, global cooling, widespread extinctions, and sweeping ecological reorganization repeatedly tested this family of sharks. Every time, survival depended less upon strength than upon adaptability. The lineage flourished because each dominant predator remained flexible enough to exploit changing oceans instead of remaining tied to a single ecological strategy. Megalodon encountered a different kind of challenge. No asteroid struck the planet, no single disaster abruptly erased marine life. Cooling seas developed gradually, productive coastal habitats diminished. Many large baleen whales declined, while surviving species became faster, colder adapted, and increasingly capable of escaping into deeper waters. At the same time, great white sharks expanded across regions that Megalodon gradually abandoned. Their smaller bodies required far less food and tolerated colder environments with greater efficiency. Early members of the killer whale lineage also appeared, adding new competition for large marine mammals already becoming less abundant. Unlike its ancestors, Megalodon possessed few practical responses. Its immense body required enormous meals. Its dependence upon warm coastal habitats limited where populations could persist. Evolution can reshape species, yet meaningful anatomical change unfolds across countless generations, not within a single lifetime. Environmental transformation outpaced the flexibility that had once defined this remarkable family. The mathematics of survival became unexpectedly unforgiving. Every ancestor had overcome crisis by remaining the more adaptable version of its ecological role. Megalodon achieved unmatched dominance, yet in doing so became the least adaptable member of the most resilient shark lineage Earth had ever produced. The very qualities that elevated it above every predecessor gradually removed the options that had always carried the family safely through a changing world. Evolution does not hand out gifts without asking for something in return. Every successful adaptation carries a hidden price, even when that cost remains invisible for millions of years. The long history of the Megalodon lineage can be read as a sequence of exchanges, each generation surrendering a little flexibility while gaining greater mastery over its environment. Those gradual bargains eventually produced the largest predatory shark the oceans had ever known, yet they also narrowed the range of futures that remained available. One of the clearest examples lies within the teeth. Early members of the lineage, beginning with Cretalamna, possessed small side points called cusplets beside the central tooth. These structures improved the ability to seize struggling prey before swallowing or tearing it apart. They remained present through most of the family's history because they continued serving a practical purpose. As hunting shifted toward increasingly massive marine mammals, however, those additional points became less valuable. Megalodon abandoned them entirely. Its prey no longer needed to be held with precision. Enormous jaws and deeply serrated cutting edges accomplished the task far more efficiently. The cutting surfaces themselves reveal another exchange. The smoother teeth of Cretalamna functioned well across an exceptionally broad diet that included fish, reptiles, and many other marine animals. Generation after generation, the edges became more strongly serrated as whales assumed greater importance within the ecosystem. By the time Megalodon appeared, each tooth had become an instrument specialized for slicing through thick blubber, dense muscle, and heavy connective tissue. The lineage sacrificed broad usefulness in favor of extraordinary performance within one particular hunting strategy. Body size followed the same pattern. Every increase in length strengthened the bite, extended hunting capability, and discouraged potential competitors. Those benefits came with rising energetic demands. Larger bodies consumed greater amounts of food, even during ordinary daily activity. When giant whales flourished across warm oceans, that requirement posed little difficulty. Productive seas could support predators of exceptional size. Once prey numbers diminished, however, the same anatomy demanded more nourishment than changing ecosystems could consistently provide. The advantage and the burden had always existed together. Its method of reproduction likely reflected similar compromises. Fossil discoveries from coastal nursery areas suggest that Megalodon invested heavily in relatively few young, each beginning life at an impressive size after extended development within the mother. Such offspring probably enjoyed better survival during favorable times than the tiny young produced by many smaller sharks. Population recovery, however, depended upon slower reproductive cycles. Declining numbers, therefore, required much longer to replace, reducing the species' ability to recover from prolonged environmental stress. Across millions of years, other capabilities gradually faded from the lineage. Earlier ancestors retained the flexibility to survive largely on fish when circumstances demanded. They tolerated broader environmental conditions, occupied wider geographic ranges, and adapted more readily to shifting ecosystems. Megalodon became increasingly tied to warm coastal seas, giant whales, and stable reproductive habitats. Rapid evolutionary reductions in body size also became less achievable because immense animals reproduce more slowly and change more gradually across generations. What those exchanges purchased was extraordinary. For roughly 20 million years, Megalodon occupied the highest position within the richest marine ecosystems its lineage had ever encountered. No known predator before or since maintained such overwhelming authority across so many oceans for so long. Natural selection had shaped an animal almost perfectly matched to its age. The bargain succeeded for as long as the world honored its conditions. When oceans cooled, coastlines retreated, and prey communities transformed, the same adaptations that once defined greatness became lasting constraints. Evolution had fulfilled its promise completely until Earth began writing a different chapter. Every fossil carries two stories. One belongs to the animal that once lived, while the other belongs to the people who spent generations trying to understand it. The lineage leading to Megalodon has revealed itself piece by piece through countless isolated teeth, each one adding another sentence to a scientific narrative that unfolded across nearly 200 years. As discoveries accumulated, the history of these sharks became inseparable from the history of paleontology itself. The modern chapter began in 1843 when the Swiss naturalist Louis Agassiz published his landmark work describing fossil sharks. Working almost entirely from teeth, he named Cretalamna appendiculata and also assigned the giant extinct shark to Carcharodon Megalodon. The decision reflected the evidence available at the time. Megalodon's broad, triangular, serrated teeth closely resembled those of the living great white shark, making a close relationship appear entirely reasonable. Without complete skeletons to compare, tooth shape served as the strongest guide for classification, and Agassiz's interpretation influenced scientific thinking for generations. As museum collections expanded and additional fossils emerged from many parts of the world, researchers noticed details that tooth shape alone had concealed. The internal enamel microstructure differed from that of great white sharks. The roots followed their own distinctive pattern, and fossil species filled the geological record with a gradual sequence of changing tooth forms extending far beyond the appearance of modern white sharks. These observations divided paleontologists into two competing schools of thought. One continued supporting a close relationship with the great white, while the other argued that Megalodon belonged to its own ancient, evolutionary branch. The discussion continued for well over 100 years because every new discovery illuminated part of the puzzle without immediately resolving it. A significant breakthrough arrived in 1964 when Soviet paleontologist Lev Semenovich Glickman proposed placing Megalodon within the Otodus lineage. Instead of focusing upon one spectacular species, he examined the complete progression of fossil teeth spanning millions of years. Small anatomical changes linked one form to the next with remarkable consistency. The sequence suggested that Megalodon represented the final known stage of a lineage that had begun long before the first true great white sharks evolved. His proposal reshaped the direction of later research and encouraged scientists to view the lineage as an uninterrupted evolutionary continuum. Modern analytical techniques eventually supplied the evidence. Earlier researchers could only imagine. Between 2012 and 2019, several phylogenetic investigations combined cladistic analysis with detailed studies of enamel microstructure and other anatomical characteristics preserved in fossil teeth. Independent teams repeatedly reached the same conclusion. Megalodon belonged within the Otodus lineage. Many leading scientific publications consequently adopted the name Otodus megalodon, although the older name Carcharocles megalodon remains common in books, museums, documentaries, and popular discussion because of its long historical use. The genus name carries an unexpected irony. Otodus comes from Greek words meaning ear-shaped tooth, inspired by the prominent ear-like cusplets found beside the crowns of early species such as Otodus obliquus and Otodus auriculatus. Those distinctive structures gradually disappeared during the lineage's evolution, leaving mature megalodon teeth without the feature that inspired the name itself. One fossil specimen has proven especially valuable for understanding that evolutionary journey. An Otodus angustidens individual from New Zealand, dating to approximately 26 million years ago, preserves 165 associated teeth together with 35 vertebral centra. It remains the most anatomically complete reconstruction available for any member of the lineage apart from Megalodon, offering an extraordinary bridge between scattered fossils and the living animal they once formed. The fossil itself has never changed. What has changed is the way scientists have learned to read it. During the past decade, shark teeth that once revealed little more than shape and size have begun offering chemical records preserved since deep time. Hidden within the crystalline structure of fossil enamel lies information that survives long after soft tissues disappear, allowing researchers to examine the lives of extinct predators with a precision that earlier generations could scarcely imagine. One of the most significant advances comes from a technique refined during the 2010s that measures enameloid bound nitrogen isotopes, commonly expressed as delta nitrogen 15 within scientific literature. Unlike proteins and other organic tissues that decay or become chemically altered after burial, nitrogen trapped inside the mineral structure of shark tooth enamel remains remarkably stable. The crystalline framework protects this chemical signature from the geological changes that often erase biological information. As a result, fossil teeth can preserve an authentic record of feeding behavior across millions of years. These nitrogen values reveal an animal's trophic level, its position within the food web. Every step upward through the chain of predators leaves a measurable enrichment of the nitrogen signal. Animals feeding upon herbivores display lower values than predators consuming other predators. The highest readings belong to species occupying the very top of marine ecosystems. Instead of relying only upon tooth shape or bite marks preserved on fossil bones, scientists can now identify dietary position through direct chemical evidence recorded inside the tooth itself. The results for this lineage have proven especially revealing. Studies of Otodus angustidens recovered average nitrogen isotope values of approximately 23.8 parts per thousand, placing this shark firmly among the highest trophic levels known from ancient oceans. Such measurements demonstrate that it regularly hunted marine mammals already occupying advanced positions within the food chain. This conclusion no longer depends solely upon anatomical interpretation or ecological reconstruction. The chemistry preserved inside the enamel independently confirms that these sharks functioned as apex predators. Other isotopes provide a different perspective. Oxygen isotope ratios, preserved within shark enamel, reflect the temperature of surrounding seawater during tooth formation. They can also preserve evidence of the shark's own body temperature when internal heat production exceeded that of the surrounding ocean. Comparisons across the lineage suggest a gradual increase in regional endothermy, allowing core muscles, the brain, and sensory organs to remain warmer than nearby water. Such physiological control likely improved swimming performance and hunting efficiency in warm environments while increasing dependence upon climates capable of supporting that elevated metabolism. Growth history has also become more accessible through chemical investigation. Vertebral centra accumulate annual layers throughout a shark's life, preserving patterns that can be examined with isotopic techniques alongside structural analysis. These growth records indicate that Megalodon required many decades to achieve full adult size. Such prolonged development meant each generation represented a substantial biological investment, reinforcing evidence that replacement of declining populations would have proceeded gradually after environmental disruption. The frontier continues advancing beyond anatomy and isotopes alone. Researchers are now exploring proteomics, the study of preserved protein sequences retained within fossil tooth enamel. Although far more challenging than conventional analysis, these microscopic biochemical remnants may eventually clarify evolutionary relationships with unprecedented confidence. Instead of comparing only tooth shape or skeletal characteristics, scientists may reconstruct ancestry through molecular signatures carried across deep time. Each newly developed technique adds another layer to the story. The lineage that once seemed known only through scattered teeth continues revealing unexpected details, proving that even the oldest fossils can speak with new voices when science learns another way to listen. Few questions surrounding this lineage capture the imagination quite like its appearance. Teeth survive in extraordinary numbers, yet the rest of the skeleton is preserved only in fragments, leaving paleontologists with an unusual challenge. They can estimate bite force, feeding style, and evolutionary relationships with growing confidence, while the outline of the animal itself remains partly concealed. Every illustration, museum mount, and documentary animation represents a careful reconstruction built from evidence mixed with informed interpretation. For much of modern paleontology, the solution appeared straightforward. Since the great white shark is the largest living member of the mackerel shark group and possesses broad serrated teeth resembling those of Megalodon, artists reconstructed the entire lineage using the great white body plan. The resulting animal displayed a streamlined, torpedo-shaped body, a pale underside, darker upper surfaces, and a large crescent-shaped tail designed for powerful swimming. That image became deeply familiar through books, museum exhibits, films, and educational programs, eventually shaping the public's mental picture of Megalodon and its ancestors. As evolutionary understanding improved, that familiar reconstruction became less certain. Fossil evidence increasingly demonstrated that the lineage leading to Megalodon did not descend from the great white shark. Instead, its ancestry traced back through sharks such as Cretalamna, Otodus obliquus, and successive members of the Otodus lineage. Similar teeth between Megalodon and the great white now appear to represent convergent evolution, with unrelated lineages independently developing comparable cutting tools after adapting to similar prey. Tooth resemblance, therefore, does not guarantee identical body proportions. This realization has encouraged researchers to reconsider how these extinct sharks may have moved through the ocean. In 2020, a study published in Science Advances reconstructed Megalodon using an enlarged version of the great white shark as its principal model. The approach provided an important framework for estimating body dimensions and swimming performance. Even so, several researchers, including Philip Stearns, have pointed out that simple enlargement may not accurately represent an animal that reached such extraordinary size. As bodies become dramatically larger, proportions often change. A broader midsection, modified fin dimensions, and altered hydrodynamics could have supported efficient movement while reducing energetic demands imposed by immense mass. Color presents an even greater mystery. Fossils preserve mineralized tissues exceptionally well, yet skin pigments and soft tissue almost never survive across millions of years. No direct evidence reveals whether members of this lineage displayed gray, bronze, black, white, or any combination of shades seen among living sharks. Every painted reconstruction, no matter how carefully produced, reflects artistic interpretation instead of preserved biological evidence. The familiar dark back and pale belly remain plausible because many open ocean predators share similar camouflage, though certainty remains beyond reach. Attention has also turned toward the shape of the snout. Some paleontologists suggest that early species such as Otodus obliquus possessed a blunter profile than the pointed snout of the great white shark. Their proposal draws upon jaw mechanics and the arrangement of fossil teeth rather than preserved cartilage. This interpretation appeared prominently in the documentary series Life on Our Planet, where paleontological consultation guided the reconstructed head shape. Although debate continues, Such models remind us that subtle anatomical differences may have distinguished this lineage from its modern counterparts. The teeth themselves still provide valuable clues. Their arrangement allows scientists to estimate jaw circumference with reasonable confidence, even though complete jaws remain unknown. The largest reconstructed megalodon jaws may have exceeded 12 feet in circumference, while Otodus angustidens probably measured between 6 and 7 feet. These figures remain carefully reasoned estimates, grounded in fossil evidence, while acknowledging that the complete appearance of these remarkable sharks still awaits further discovery. Scientific names often appear permanent, as though they mark clear boundaries that have always existed. The fossil record tells a more fluid story. Each newly discovered tooth can strengthen an existing classification or blur the lines separating one species from another. Within the lineage that ultimately produced Megalodon, this uncertainty has inspired one of the most thoughtful debates in paleontology, reaching beyond anatomy into the meaning of evolution itself. Traditional classification divides the lineage into familiar stages. Otodus obliquus gives way to Otodus auriculatus, followed by Otodus angustidens, then Otodus chubutensis, before finally arriving at Otodus megalodon. Each name reflects recognizable differences in tooth shape, body size, serration, and geological age. This approach provides practical categories that help scientists organize fossils recovered from different rock layers across the world. Museums, research papers, and educational collections rely upon these names because they create a consistent language for describing evolutionary change. Some paleontologists have proposed that nature may not have recognized these divisions at all. During 2001, paleontologist Michael Benton discussed the concept of chronospecies, a framework describing species that transform gradually through time without sharp biological boundaries separating one form from the next. Under this interpretation, the members of the Otodus lineage could represent a single evolving species expressed across approximately 60 million years. Every generation differed only slightly from its parents, producing continuous change too gradual for any individual animal to perceive during its own lifetime. Viewed through that lens, no single moment marked the disappearance of Otodus obliquus or the arrival of Otodus auriculatus. There would have been no generation in which parents belonged to one species while their offspring belonged to another. Each population inherited subtle variation, and those differences accumulated across immense spans of time. The boundaries recognized today would therefore represent convenient markers created by scientists attempting to describe a continuous biological flow instead of distinct natural breaks. Many researchers continue supporting the traditional classification for compelling reasons. Tooth morphology changed substantially throughout the lineage. Early members possessed prominent cusplets beside the main crown, while later forms developed broader cutting surfaces and eventually lost those structures altogether. Body size increased dramatically, feeding ecology shifted toward progressively larger prey, and anatomical differences accumulated over millions of years. An Otodus angustidens living around 30 million years ago would likely have differed so greatly from a megalodon living approximately 5 million years ago that placing both within separate species remains scientifically useful. The modern placement of Megalodon within the genus Otodus carries significance beyond taxonomy alone. Earlier classifications separated the giant shark into its own distinct genus, emphasizing its uniqueness. Restoring it to Otodus recognizes an uninterrupted ancestral connection stretching deep into Earth's past. The name itself acknowledges that Megalodon did not appear suddenly as an isolated marvel. It emerged through a continuous sequence of inherited changes extending across countless generations. This perspective also reshapes the idea of ancestry. Calling Otodus angustidens, or Otodus chubutensis, an ancestor of Megalodon remains scientifically accurate, yet the description carries an element of human convenience. Those animals occupied earlier chapters within the same unfolding lineage. Looking farther back, even Cretalamna becomes part of that gradual transformation. Across roughly 100 million years, evolution never paused to announce a new beginning. Life continued adapting one generation at a time, while the names applied by science traced reference points along an uninterrupted river of change. Evolution leaves no monuments, only descendants and fossils. Looking back across the immense history of the Otodus lineage, one thought gradually rises above the details of teeth, anatomy, and geological ages. After nearly 100 million years of continuous change, did this lineage ultimately produce its greatest achievement, or did it arrive at a form so specialized that it could go no farther? The answer depends entirely upon the measure chosen to define success. Measured by power alone, Megalodon occupies a place unlike any other known marine predator. No earlier shark combined such extraordinary size with immense bite force, worldwide distribution, and the ability to hunt some of the largest animals living in the sea. For approximately 20 million years, it dominated marine food webs across much of the planet. Few predators in Earth's history maintained such influence over so many oceans for so long. Its teeth, preserved by the thousands, testify to a period when one evolutionary experiment reached a level of predatory performance unmatched before or since. That achievement did not emerge suddenly. Every earlier member of the lineage contributed another small step toward it. The broad cutting edges, stronger jaws, increasing body size, and changing prey preferences accumulated gradually across millions of generations. Each adaptation proved effective within its own environment, allowing descendants to inherit a foundation upon which further changes could build. Seen from that perspective, Megalodon represents the culmination of a remarkably persistent evolutionary direction that stretched across deep time with astonishing continuity. A different picture appears when survival itself becomes the standard of comparison. Earlier relatives endured repeated global disruptions without disappearing. Cretalamna survived for roughly 50 million years, while Earth's climate, coastlines, and marine communities transformed around it. Other members of the lineage also persisted through changing oceans by maintaining broader ecological flexibility. Megalodon, despite possessing unmatched predatory ability, became the first member of this long succession unable to adapt when environmental conditions shifted beyond the limits of its specialization. The qualities that elevated it to extraordinary success also narrowed the range of circumstances under which it could continue thriving. This contrast reveals an enduring pattern within evolution. Specialists often flourish when ecosystems remain stable and resources consistently support their particular adaptations. Their refined abilities allow them to dominate ecological roles with remarkable efficiency. Generalists rarely achieve such overwhelming dominance, yet they possess broader options when familiar conditions disappear. Flexibility becomes a form of resilience, preserving lineages through periods that overwhelm more narrowly adapted organisms. Across the history of Otodus, both strategies appeared, each carrying distinct advantages and unavoidable costs. The modern classification placing Megalodon within the genus Otodus quietly reflects that broader story. Although individual species names help describe changing anatomy through time, the shared genus recognizes an enduring continuity extending far beyond any single animal. Megalodon remained part of the same unfolding lineage that began with far more modest ancestors. The giant predator did not stand apart from them. It represented one expression of an evolutionary process that had never truly stopped. Perhaps that is the deepest lesson preserved within these fossils. Biological success cannot be measured by only one scale. Strength, longevity, adaptability, and ecological influence each illuminate different parts of the same history. The lineage produced organisms capable of surviving immense planetary change, and eventually one capable of ruling ancient seas with unmatched authority. Together they reveal that evolution does not pursue perfection. It continually explores possibility, allowing time itself to determine which paths continue and which eventually come to rest. No living shark carries this lineage forward. Its branch ended millions of years ago, leaving no direct descendants cruising today's seas. Even so, disappearance is not the same as absence. The influence of these predators continues within the structure of modern marine ecosystems, woven into the lives of animals that evolved alongside them. Their inheritance survives not through bloodlines, but through the lasting imprint they left upon the ocean itself. One of the clearest examples appears in the modern great white shark. At first glance, its broad, serrated teeth resemble those of Megalodon closely enough to have confused early paleontologists. Modern research has shown that this resemblance arose independently. The great white belongs to the genus Carcharodon, following a separate evolutionary history. After Megalodon vanished, however, great white sharks expanded into ecological opportunities that had once belonged to the Otodus lineage. This transition illustrates ecological succession, with one predator gradually occupying a role that another had maintained across tens of millions of years. That change affected far more than a single species. Sharks living today evolved while members of the Otodus lineage dominated warm oceans across much of the globe. For nearly 100 million years, countless marine organisms developed beneath the constant presence of these apex predators. Every generation of prey encountered selection pressures shaped by the possibility of becoming food. Greater speed, sharper awareness, coordinated group behavior, and improved escape strategies all carried survival value in seas where enormous hunting sharks remained a persistent feature of everyday life. Marine mammals experienced particularly strong evolutionary pressure. Early whales entered oceans already occupied by these formidable predators, and their descendants continued sharing those waters for approximately 60 million years. As whales diversified, traits that reduced predation risk became increasingly valuable. Greater swimming speed improved the chances of escape. Deeper diving opened environments that large predators visited less frequently. Expansion into colder waters also created refuge beyond the preferred habitats of many members of the Otodus lineage. The remarkable abilities of the blue whale and the sperm whale developed through many influences, yet long exposure to giant predatory sharks almost certainly formed part of that evolutionary landscape. Large fish likewise responded to this ancient ecological balance. Schooling behavior, streamlined bodies, and rapid bursts of acceleration became essential tools within food webs governed from above by highly capable hunters. Even predators occupying intermediate positions evolved beneath the influence of an apex competitor whose presence shaped opportunities throughout the ecosystem. The effects spread outward through entire communities, influencing interactions that continued long after individual species appeared or disappeared. Evidence of this enduring history remains scattered across the world. The phosphate deposits of Morocco preserve countless teeth from successive members of the lineage. Limestone formations in Kansas record another chapter of their existence beneath vanished inland seas. Chalk deposits in Alabama contain additional traces, while marine sediments in New Zealand preserve later representatives approaching the end of their remarkable history. Across continents separated by thousands of miles, the same distinctive teeth appear again and again, marking nearly every warm ocean that existed during the lineage's long reign. Together, they form a geological memory written into Earth's rocks. The oceans surrounding us today, therefore, occupy an unusual moment in planetary history. Only about 3.6 million years have passed since the final confirmed appearance of Megalodon, scarcely more than an instant on the geological timescale explored throughout this story. Modern seas contain extraordinary diversity, yet one of their longest reigning predators is missing. The rhythms of today's marine world were shaped across 100 million years by animals that no longer swim beside us, leaving an ocean defined as much by enduring influence as by present life. A single fossil tooth can seem like the entire story until the passage of time is placed beside it. Stretch the history of this lineage across one ordinary day, beginning at midnight with its earliest ancestors and ending at the final disappearance of Megalodon, and an unexpected picture appears. Megalodon does not arrive until approximately 10:40 in the evening. Nearly the whole day belongs to the generations that came before, each one carrying the lineage forward through changing worlds that never paused for them. Seen from that perspective, this has never truly been the story of one famous shark. It has been the history of a dynasty whose members inherited, refined, and passed onward an evolving design across almost 100 million years. Every tooth displayed beneath the name Megalodon carries the accumulated work of countless ancestors. The broad crown, the strengthened root, the cutting edges, and the immense proportions did not emerge in a single moment. They represent the final expression of a pattern shaped gradually through millions upon millions of births, hunts, and surviving descendants. That longer view also changes the meaning of the title itself. Calling one of Megalodon's ancestors more terrifying does not suggest greater size or greater violence. Those earlier sharks entered oceans that offered no established blueprint for becoming the dominant marine predator their descendants would eventually become. They encountered unfamiliar prey, formidable competitors, and ecosystems still recovering from earlier upheavals. Through persistent adaptation, they established a way of life that later generations inherited. The greatest gift passed to Megalodon was not extraordinary anatomy alone. It was an ecological foundation patiently assembled across immense spans of evolutionary time. The final heir became magnificent because those earlier generations endured every challenge placed before them. They persisted beyond the disappearance of giant marine reptiles. They survived the Cretaceous-Paleogene extinction that transformed life across the planet. They adapted through warming oceans, cooling climates, changing coastlines, and shifting food webs. Each surviving population preserved possibilities that future descendants could explore. Without those earlier victories, Megalodon would never have existed. The celebrated giant therefore stands less as an isolated marvel than as the visible summit of a mountain whose base extends far beyond ordinary imagination. Perhaps the most remarkable figure within that history is not the largest member at all. Picture Cretalamna, measuring roughly 12 feet in length, swimming through seas 100 million years ago. Around it lived predators capable of hunting sharks, marine reptiles unlike anything alive today, and unfamiliar fishes occupying ancient ecosystems. Nothing guaranteed that this modest ancestor would leave descendants stretching almost to the present day. Yet generation after generation survived, carrying forward small inherited changes that accumulated with extraordinary patience until they eventually produced the lineage's greatest giant. Then, during the final moments of that 24-hour clock, the long succession reached its conclusion. Cooling oceans, changing prey, and narrowing ecological opportunity finally overcame a family that had endured almost everything Earth could impose. No dramatic ending marked the last chapter. The lineage simply ceased, leaving behind scattered teeth resting within sediments that would one day rise into cliffs, deserts, and mountains. Today's oceans remain filled with remarkable life, yet they also preserve the shape of something no longer present. The deepest legacy of this dynasty is not found in a single fossil or museum collection. It exists within a marine world molded across 100 million years by predators whose story still echoes through every sea, long after the final swimmer passed beyond the horizon of geological time.